linearized stability for Euler. And so I decided, instead of showing the computations immediately for the case that we have considered, I will show you some easier and classical computations about hydrodynamical stability in 2D. I will show how that leads to some second order ordinary differential equations. And that will allow me later to not do the computation, but convince you how things come into play and what are the new difficulties that arise. Okay. So I will start by some very basic textbook computations on hydrodynamical stability for shear flows and for stratified fluids. Okay. So let me start, but I will stress what will remain when we will discuss columnar vortices. So let me start with instability for shear flows in 2D, and how you prove that classically of shear flows. So I'm still here considering dtu equals plus u modulo u is equal to minus grad p, but here in 2D. And the divergence of u is equal to 0. And I will consider a shear flow, so a flow that looks like this. Well, shear in the y, in the x. So I will put it x, y. And it's classical to make this picture. All textbooks have the same profile for the velocity. So this is just the envelope of the velocity field. Okay. So let's take a velocity field which has this form. So there are stationary solutions that have this form, stationary. You take u, let me call it u naught of x and y, is u, capital U, this is this profile, capital U of y along x only, okay? And p is 0 in that case, p0 of and t of x, y, t is a constant, or say 0. So this is a stationary solution for an arbitrary profile capital U. And now we are going to linearize around this special profile. Linearize. So I'm going to consider how to replace. I'll take U, which is U naught, plus a U tilde, and the P, which is P naught plus P tilde. And I skip the quadratic terms in U tilde and P tilde when I plug that into the Euler equation. And if you don't mind, I remove the tilde as well, because otherwise it becomes painful. So the linearized equation will be dtux plus U of y ux, dx ux, sorry, plus capital U prime of y times uy is equal to minus dxp. The second one is similar with one term missing, plus capital U of y dy, sorry, dx uy is equal to minus dyp. And I still have the divergence free condition. So dx ux plus dy uy, this is a linear one, is equal to 0. Okay. So now I'm taking into advantage the fact that my setting is a translation invariant in the x direction. So I'm going to take Fourier in x. Take Fourier in x. Which means that I will just replace the dx by I times k. Okay, this is remember k. And I will then consider linear stability. So I'm considering eigenmodes. I will look for eigenmodes. So I replace also the time derivatives. I replace the dt by the eigenvalue. Okay, so let me call it S. And in principle, it could be complex because this linearized system is not self-adjoint, not square-adjoint either. Okay, so when you do that, you have a simpler system. And I'm going to introduce this function because that will happen from these four terms here, gamma of S, which is just S plus IKU, okay, Y. So sorry, it's gamma of Y. And so we get gamma of Y times UX plus U prime of Y times UY is equal to minus IKP, and gamma of Y UY is equal to minus dy of P. And finally, I have the divergence free relation, IK UX plus dy UY is equal to 0. Okay, these three things. Now from these three, so this is a system. This is the eigenvalue system. I can write a single equation for Uy, because you see from this relation, I can isolate Ux as a function of the derivative of Uy. I plug it in here. Okay, so I remove the Ux, it becomes a derivative, a term with a derivative of Uy. And the pressure, I then eliminate it from these two. I take the y derivative of this term, and I will have a second order ODE with only Uy. Okay, I write it here. It's called the, oops, sorry. It's called the Rayleigh equation. You get the Rayleigh equation. Which I did the computation for you, is the following. D2y Uy plus k square Uy plus, so it's there's a complex term here, ik u second of y over this gamma that I defined just before, gamma of y times Uy is equal to 0. Okay, and now you multiply by Uy bar, and you integrate by part, plus integration by parts, and then you get that this quadratic relation, dy Uy squared plus k squared, so this looks fantastic from the start, Uy squared plus ik, put gamma bar here, u second of y over gamma squared times Uy squared. And this has to be equal to 0 if the solution is sufficiently localized, but we are looking for localized mode. Let me do the computation formula. Okay, so what does that give us? You see, it looks like we should look for the real part here, because that's where we have something positive. There you want to say something like, I have a positive constant that must be equal to 0, therefore it must be 0. The real part is appealing here because we have this, but recall gamma is S, which a priori is in C, S, plus I, K, U of Y, okay? So the real part here is not going to be really helpful, because I should need to consider the imaginary part from this gamma bar here. But if I look at the imaginary part, at first I have S, well, the real part of S. Okay, so now if I take the imaginary part of this thing, I'm gonna have the real part, that's gonna be the real part of S, times the integral of what? I'll have a K, U second of Y over this gamma squared and this Uy squared, okay? So we see that if this U second is of constant sign, then this quantity can only be 0 if Uy is identically 0. Okay, so if U second is of constant sign, we conclude that there are no eigenmode with real part of S different from 0. Okay? There may be purely imaginary mode, but no matter. In particular, there are no unstable mode. Okay? So Rayleigh, I forgot an H here. So this is the classical, and it's called the inflection, the no inflection point theorem. It's attributed to, depending on the books, to Rayleigh, and sometimes it's called also the Arnold, Rayleigh-Arnold criterion. Okay, so that was for shear flows. And so remind ourselves what we did. We started from a stationary solution. We looked at the perturbation. We went into Fourier. We obtained a second order ODE. And from this second order ODE, we built a quadratic form, which we showed could not have zeros, okay? Non-trivial zeros. So that's the idea of these classical computations. Let me do a second one of the same nature. That's for the Rayleigh-Taylor instability. Different setting that will yield a different criterion. And we will then see that our criterion is kind of a combination of both. Rayleigh-Taylor instability. So here it's for stratified fluids. So the setting is slightly different. So I take a fluid. Let me try to draw a picture like this. So I have my X and Y, and maybe I have a fluid that have, let's say, maybe more density here at the bottom, that here at the middle, and here less than here. Okay. So I couple the equation for the velocity with an equation for the density. So the fluid is still incompressible. There will still be the divergence-free condition, but now I have a density rho, which is transported by the flow. Okay, so equal to 0, and rho times dtu plus u u is equal to minus gradient of the pressure. And now I put also the gravitational force to get some interesting solutions. Otherwise, density is of few importance, and divergence of u is equal to 0. Now, my reference in that case, my reference solution, so my reference stationary solution, will be an arbitrary function of the height. So rho of x and y is actually a function of y only. And let me take the 0 speed as the reference solution. So you can do the same, you can play the same, game. Exactly the same game. And you can also build an equation for the velocity. So you get a second order equation for also for uy in this case, for uy, which is the following. It's also called the Rayleigh equation. So it's minus dy rho naught of y ds uy plus k squared rho naught of y uy minus k squared rho naught prime of y over s squared times uy is equal to 0. Again, you multiply by uy bar, you integrate by parts, blah, 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 and you get this identity integral of rho naught ds uy squared plus this positive part remains the same, rho naught of y uy squared minus k squared rho prime uy squared over s squared, okay, is equal to 0. Okay, and again, so this is a rho prime now. Again, we will look at the the imaginary part of this equation and deduce that if rho 0 prime is negative, then there is no unstable mode. Okay, so why? It's maybe a little bit more intricate because you have this S squared here. Okay, so we should look maybe both at the real and imaginary part. Okay, well, first, as before, if rho prime is of constant sign, if rho 0 prime is of constant sign, I'm going to have no non-trivial solution if 1 over S squared has a non-trivial imaginary part. Okay, as a non-trivial imaginary part. So this only gives me the real 1 over S squared as a non-trivial imaginary part. Sorry. Yes, so if rho prime is negative, in particular, rho prime is of constant sign, therefore, if 1 over S squared as a non-trivial imaginary part, there cannot be solutions because I have something non-zero times something which has a constant sign that has to be equal to 0, then that cannot work. But there could still be eigenvalues with real S, okay? And in that case, I'm going to use the sign. It's not just different from 0. Here I've assumed that it is negative. So when S is real, 1 over S squared is going to be positive. And so if this is negative, now I'm going to have a positive quantity. And now I have to use this positivity here too. So the real part, okay, positive plus positive cannot be equal to 0. So I have to distinguish the two cases. So if the heavy fluid is on the bottom and the light fluid is on the top, I have no unstable mode. But on the other situation, I could have unstable mode. Actually, there should be some unstable mode if you think in terms of Sturm-Liouville theory. If there's a point for which rho 0 prime is positive, then if you take S sufficiently small, you can certainly take a function for which this is going to be very negative. Okay, so the quadratic form will be negative. And then you grow a little bit S until it becomes equal to 0. Okay. So this is the Rayleigh-Taylor instability. Now we are going to mix both. So in both cases, what happens is that you get a quadratic form and you can derive a direct contradiction to the existence of an unstable mode from this quadratic form. So let's mix both, as I said. Now we are going to take shear flows in stratified fluids. That will be the Kelvin-Helmholtz instability. Kelvin-Helmholtz instability. Okay, so again, the equation is dt rho plus u rho is equal to 0 and rho dtu, but I'm going to start from a different minus gradient p plus rho times the gravity constant times ey, and it should be a minus, not a plus. Gravity is going down. Okay. So x, y. Now I have my laminar flow here, shear flow, but on top of them I have a varying density. And the two phenomena are actually orthogonal. So at the level of stationary solution, you can add the two. stationary. You can take u, rho, which is an arbitrary function of y, and you can take u, a little u, which is an arbitrary function of y along Ex. So this is still going to be a stationary solution for arbitrary rho naught and capital U. And the pressure is just, it just obeys that its derivative is given by minus rho 0 times G. It's the gravity constant. So for arbitrary rho naught and capital U, this is a stationary equation. Again, you play the same game. You see, the problem is still invariance by translation along the X. So you can still take Fourier and blah, blah, blah. And you get a second order equation, which I write now, minus dy. It has the same form as the previous one, but now there is the additional, it's a mixing of both if you want. Plus k squared rho naught uy plus ik over gamma rho naught. So all the computation that I skip should be immediate, well, trivial. There's no trick. I have them on my notes, but if I realized if I do them on the blackboard here, it's too slow for the lecture. But there's no missing tricks. It's only straight computations. K squared G rho naught squared over gamma squared uy is equal to 0. Okay, so that's the Rayleigh identity, the Rayleigh ODE for stratified fluids with a shear flow. And you can try to do the same trick as before, multiply by uy, etc., uy bar, and derive some contradiction. And it seems very difficult to obtain anything because of these two terms. You see, they are very different nature. I recall you gamma of y is s plus ik capital U of y. Because of this gamma square here and this gamma, one being multiplied by a complex and the other one not, there is no clear way to put a sign out of this ODE. Okay, this complex valued ODE. So that's where there's another trick appearing when you can't obtain, say, the positivity of a quadratic form when it doesn't show clearly. Sometimes there are some clever change of variables that make the quadratic form appears cleaner, and that's what. So here, for example, I'm following a paper by Louis Howard and Gupta in the 60s, where this computation was done. And they had the idea from this Rayleigh ODE to consider not the function u, but make this special change of variable. So you replace uy, so you write uy as this spectral function, let me call it the spectral function gamma y at the power 1/2 times v. And now you write the equation for v. Okay, so in their paper, they have a lot of change of variables in order to derive as much information as possible on unstable modes. And they end up with this one, which is the nicest one, which yields the following equation, which yields the equation minus, let me skip the y now and just put primes on the functions. It will be quicker to write, but still this second order equation, k squared rho naught gamma v plus ik over 2 rho naught u prime v. So it's always a second order term plus a 0 order term. There's never first order term. Say you find the correct Sturm-Liouville form so that there is only a 0 order term here. Gamma prime squared minus k squared g rho naught prime over gamma. And this is also over gamma. Over 4 gamma times v, sorry. So a second order ODE, but now this the problem that we have before with this gamma and gamma squared has disappeared, and we can build things up so that this quantity now will have a sign. So if you do the same multiply by V bar, blah blah blah, you get this relation. You get, and you take the real part plus take the real part as we did before. You get that the real part of S times the integral of something positive, so rho naught plus, this is the H1 norm here. So let me put it quickly, V prime plus V squared. There's a K squared here. I should keep the plus still something positive, K squared rho naught U prime squared over gamma squared, but something real, positive, times what I will call the Richardson number of y minus 1/4 times v squared. Okay, so I will write on the next slide what is this real function Ri. It depends on our initial two choices, rho naught and capital U. But now we have a quadratic form which clearly has a sign if this quantity here is larger than 1/4. Okay, so their clever change of variable put back things with a quadratic form, which is much more pleasant. Okay, so that's the second trick I wanted to show here. So the first trick is reduce the linearized eigenvalue equation by Fourier to a system that you can reduce to one ODE and build a quadratic form out of this ODE for which you can show positivity. And the second trick is when this doesn't work, sometimes there are some nice changes of variable that can make the same quadratic form looks in a different way and in a better way where you can see some positivity. Okay, so in particular from this, so this Ri of y is minus G rho naught prime divided by rho naught U prime square. So in physics term, okay, this is the stratification, the derivative of the density. Okay, I will call it the stratification of the density. And this is U prime is the shear. Okay, so it's the ratio. It's actually, you see, the previous slide it was compared with 1/4. So it's a number without units. If you look at physical units, this has no unit. Okay, so it is a ratio of stratification to shear. And so what the Kelvin-Helmholtz instability result says is that if, from the previous slides, if Ri, if the Richardson number, it's called in physics, is larger than 1/4, then no instability. So you see, it means if your fluid is sufficiently stratified, for example, in the winter, with respect to the shear, then you won't have instability. And on the other way, if the weather is hot and there is shear in winds, so shear is a big difference of the speed of winds with altitude, then there will be some buoyancy in the flow. Okay? And actually, this number is really, it is what is, this Richardson number is what is computed by a meteorologist to advise airline companies when they sometimes in the cockpit, sometimes the pilots have a message that says wind shear, and that's exactly when the computation of this number is too high, because that's going to create turbulence. Actually, I have a picture. No, I showed that later. Okay. So that was for 2D situation. Now let's go to 3D situation. And what are the vortices that we are going to consider? So now I go to columnar vortices. Okay, so columnar vortices would be, let me go into cylindrical coordinates to write the flow. Okay, so I will have, I'll try to make a picture here. So I have the vector ER, the vector E theta, which will be here, and my UZ, EZ, which will be vertical here. And I'm considering a vector field, which is of the form U is, it's just circling around the cylinder. So it's a function of R along E theta. Okay, it's a circular flow, and it's the same in all the planes. It does not depend on Z. Okay, the pressure P is also a function of R, and there's a balance between the pressure and the velocity, so that the centrifugal force is balanced by the speed of rotation. So what does it have to do with the stratified fluids that I wrote before? Well, you can think that, you see here, there's a balance between the centrifugal force and the velocity of the fluid. Think of the gravitation in the stratified fluids as playing the same effect as the rotation in the circular fluids. Okay, so the centrifugal force here has to be understood a bit as the gravitational force in the stratified fluids. That's why the two will be somehow related. Okay, and so again, for an arbitrary function capital V and P in this way, this is a stationary. So this is stationary solution of Euler, well, 2D and 3D. It does not depend on Z. Euler 3D for all capital V, whatever capital V. So for the remaining, I will. There are some quantities that will play a role, so I define them. I will use the angular velocity, which is sometimes more useful than the full velocity. So angular velocity. Is omega of r, is just the velocity divided by the radius. And the vorticity, which we have written with already in the previous talks, vorticity. Let me call it capital omega, capital W here, which is, it's 1 over r. It's a bit different because we are in cylindrical coordinate, the r of r times capital V of r. It can actually be written in terms of this omega here. It's, if I remember, it's r omega prime of r plus twice omega. Okay. Okay, now let me state some classical theorem, which are in a sense the exact equivalent of the criterion, the Rayleigh criterion that I wrote in the previous slides for the 2D shear flows and stratified shear flows. So there's say Theorem 1 by Rayleigh. Also, so all these theorems are from this one, I think, is 1880. Says that if, so that's for the 2D case. So for 2D, so when I mean 2D, there is no Z component to the flow. I'm assuming a pure 2D situation. For 2D, if the vorticity, sorry, it's R here, it's not capital omega. If the vorticity is a monotone function of R, then no unstable mode. So that's for 2D. And there is a similar theorem also by Rayleigh. Well, let me put the Canadian name of Singe close to Rayleigh, because the proof by Rayleigh it's strange, because that proof from the 80s is really a mathematical proof. It goes through this Rayleigh equation, the ODE, and the proof in that one by Rayleigh was in 1917, and the one by Singe, which is a true proof for is 1933, I think. That one by Rayleigh is really a physics proof, one you would find in physics textbooks. And personally, I don't. Well, I would not buy the argument. If you are interested, look at the original paper by Rayleigh. It doesn't look mathematical at all, but still, it's always attributed to Rayleigh. It says the following: that's for the axisymmetric situation. No, in 3D, but for axisymmetric perturbation, there is no eigenmode if it's a slightly different condition if the circulation is monotone. There's a circulation along a radius. Okay, so if the way it's stated in Rayleigh is if the square of the circulation, because it might be negative, square of circulation is an increasing function of R. Okay, the circulation is 2 pi R times V of R. Okay, and it can be shown to be, so this criterion can be shown to be equivalent to the fact that what is called the Rayleigh function pi, which is twice capital omega times capital W, is positive. Okay, now I have a slide. Maybe I can just show that new share from a seminar. Here I have two pictures of what happens when one of these two criterion is not met in real life. Okay, so this is a typical picture of Rayleigh-Taylor Kelvin-Helmholtz instability. There is some layer of wind here at the bottom of the atmosphere, and a one with a different speed at the top of the atmosphere. So if you compute with respect to vertical coordinates here the vorticity, the speed goes from one constant to another constant. So the vorticity, if it was an abrupt transition, would be just a Dirac along this line. Okay, so in particular, it's not monotone because you jump to a very high constant and then you go back to 0. Okay, so this one is not satisfying the criterion of the first Rayleigh, and the instability you see here due to the clouds, you see the formation of this roll in the layer. Okay, so that's what's called a typical Kelvin-Helmholtz instability. And the failure of the second Rayleigh criterion is related to what is called the Quette-Taylor instability, and that's something you can visualize. It's more complicated. When you take two cylinders and you fill the region in between with water. Okay, and so if you rotate then the outer cylinder, the circulation is going to be an increasing function of the radius, and you are not going to see any instability. Instead, if you can rotate the inner part of the cylinder, the circulation is going to be a decreasing function of the radius. And if you rotate sufficiently fast, actually, for Euler, you could rotate. If there is no friction at the boundary, there will be no motion. So this is more appropriate to say there's a little bit of viscosity, Navier-Stokes, but in the end, it would look like an Euler flow when it's stabilized. But then if you increase the velocity of the inner cylinder, the flow would destabilize and form these bizarre donut-shaped patterns. If you look on YouTube, on the internet, and dial Quette-Taylor instability, there are some very nice videos where these donuts are forming. Okay, but these are two 2D-like situation. This is purely 2D, and this is purely axisymmetric. So there is no dependence here at the start. I mean, for the Kelvin, let me go back now to my slides. Here you assume that the perturbation is axisymmetric. So there is no theta dependence in the flow. Of course, nature will not respect that. And so what we did with Thierry Gallet is to extend these theorems for the full 3D situation, and also put some mathematical, some clean mathematical conditions. So let me maybe state the theorem. If I can find it back in my notes, and then I will give 2 words about the proof, and it will we'll go back to the first slides of this lecture. So the theorem is the following. I'm going to assume that we have the Rayleigh 1 plus Rayleigh 2. Well, no, sorry. Let me be. I said I will do some clean assumptions, so let me do some clean assumptions. I'm going to assume that capital W is a C2 function, which is decreasing. So that's the first Rayleigh criterion, and it's on R2, on R3, on the whole of R3. Okay? W prime of R is negative for R strictly positive, and we also need to assume that capital prime of R, a sufficient decay at infinity. Tends to infinity as R tends to infinity. We are mainly interested, in particular, to the Lambozine vortex. So the columnar vortices that are important or that are observed in real life, they have some exponential decay due to the viscosity, Gaussian decay. So this kind of assumption is certainly reasonable. So this is exactly Rayleigh 1 plus Rayleigh 2 with assumptions on regularity, because on the whole space the Rayleigh 2 assumption is weaker than the Rayleigh 1 assumptions. You see, the experiment that I show you was in a cylinder. It happens that on the whole plane one is stronger than the other. So it's just the fact that the vorticity is a decaying function, is a decreasing function of the radius. So we assume this, but we need to assume a second assumption. And this second assumption has something to do with the Richardson number that I wrote you before. And it's actually a Richardson function. So we are going to assume that the C2 function capital J of R, which is phi of R divided by omega prime squared of R. Okay, so phi, it's the one from the previous slide. So it's 2 omega of R times capital of R divided omega prime of R squared. Okay, so this is a second, a further assumption that we need to assume. And we assume that this function is decreasing, satisfies that G prime of R is negative for all R positive, and R, G prime of R tends to 0 at infinity. Okay, then the spectrum. So now the spectrum of, even more than the spectrum, we can say, well, let me first, yes, the spectrum of the linearized operator. So let me just write L is the linearization of Euler 3D around my vortex column. Okay, I call it capital L, and L, I view it as an operator, L being viewed as an operator from L2, from the natural energy space. So L2 with 0 divergence, with values in R3, L2 div. The spectrum of this operator is equal to the imaginary axis. So there are no unstable modes. And actually, we have a little more than that. We have an estimate, and moreover, and moreover, there is some uniformity of the resolvent along vertical lines, which is that the norm of the semi-group associated to it. So the operator norm as a function from, let me call that x, from x to x. This is, we cannot show that this is bounded, that would be the dream. We can just show that it is sub-exponential. So for it is less than an exponential of epsilon times value absolute for each epsilon. Positive. So for each epsilon, there is a constant C epsilon. So it's usually called, it says that when this happens, we say that the growth bound of the semi-group is 0. But we cannot prove, for example, that there is only polynomial growth for the mode. But still, we prove that there are no exponential mode. There are no eigenvalues. Okay, a few words about the proof. Well, the first part is you play exactly the same trick. As in Howard-Gupta, which means here we can do Fourier as well, but the Fourier has to be different. Let me write the Fourier decomposition is no longer a long variable, but here you would say that U is a U of R and T times an exponential I m theta and exponential I k z. Okay, I have two Fourier direction. I have translation against the vertical direction, and I have invariance by rotation. So I have two Fourier modes. So you play the same trick as in Howard-Gupta, and now you will get families of ODEs that depends on two parameters. You get ODEs. Second order, depending on M and K. Okay, so M is in Z, and K depends if you consider the periodic, or it could be Z, it could be R. Okay, so it's in both cases. And if you use the Howard-Gupta trick, so the same change of variable, you can obtain the following. So you obtain that if K square over M square times capital phi of R, so what I call my function capital J, omega prime of R squared, is larger than 1/4 for all R, then no unstable mode in that Fourier sector. Okay, in that Fourier sector. Okay, because it's an analysis which is done at fixed M and K. Okay. And the problem, and actually this first part was the main object of Howard and Gupta's work. The problem with this is that this condition is never going to be satisfied for all values of K and M. And actually, even if you take, so a note, if you take for omega the Gaussian, if omega of R is exponential of minus R squared, suitably normalized, so the Lambozine vortex, then it's never satisfied, because this quantity, I'll call you, this was twice omega times the vorticity. So this is a Gaussian decay. And this, even if the vorticity is a Gaussian, the velocity field is never going to be decaying. It cannot decay faster than 1 over R squared, because the circulation has to be equal to the vorticity inside by Stokes' theorem. So this will always have an algebraic decay, whether this is a Gaussian decay for the Lambozine vortex. So not only it is not satisfied for all R, but it is never satisfied. Okay. And so that was the situation after Howard and Gupta's paper, and the reason why the situation was blocked for 2D. So what's the new idea? The idea is the following. is the third trick, if you want. So in analysis, you get quadratic forms. If you are lucky, you show that something positive has to be equal to 0, and that's finished. If not, they found a nice for Kelvin-Helmholtz, they found a nice change of variable, and which shows that something is easily shown to be positive, and you are finished. And the next thing that we do in analysis when you don't see it clearly, you try to change the problem or to transform it into an easier problem. So the idea here is that if K and M are fixed, we can build a special capital omega, let me call it capital omega of MMK, for which this holds, for which, let me call it star holds. Okay, but of course for that one, star will not hold for different values of MMK, but for one specific choice of Fourier sector, we can find a vortex profile for which there will be no no unstable mode in that Fourier sector. And then you do an argument by contradiction. Then argue by contradiction and do a homotopy. So we said the following: we suppose that our original capital W has an unstable mode, has an unstable mode. Now you pick in some Fourier sector, it will be in some Fourier sector. You pick this capital MK, WMK, and make a homotopy between both. Okay, so I start and finish with that slide and just a picture. Oops. Okay, so I have my initial vorticity profile, capital W, and I will make a homotopy with a time. I will transform it into, we call it, I don't know, psi. It will depend on t, and t between 0 and 1. I will make a continuous homotopy between the two with my WMK. And now I'm looking at the complex plane where I look at eigenvalues. I look at the eigenvalues corresponding to this and to this. Well, it happens, this is part of the warm-up on the linearization of Euler, that independently of the vortex profile, or at least it's not too rough, you can show that my operator L, okay, it has a band of continuous spectrum here like that, and a possible number of eigenvalues out of the imaginary axis. But these eigenvalues, these unstable mode, if they exist, they are necessarily eigenvalues with finite multiplicity. There is some kind of, some Weil theorem into play. There is a compact perturbation of something for which you can compute explicitly the spectrum. So here, the potential unstable mode, they are eigenvalues with finite multiplicity. In particular, they depend continuously on my homotopy here. Okay, eigenvalues with finite multiplicity. So I can track them. I can track them, and I will track them up to the point here. This one, I have assumed that it has some eigenvalues. So I track them back, and sorry, no, it's the contrary. That one has no, that one has no unstable mode, okay, because it satisfies the previous criterion. My assumptions by contradiction is that this one has unstable mode, So I'm going to track them back by the homotopy up to the point where they emerge from the imaginary axis. They have to, because they are continuous from as a function of my homotopy parameter. Though at some point, it means here in the at t equal to some t star, some eigenvalue, there were no before, and some eigenvalues here emerge. Okay. So what we will do then is to look at the second order ODE corresponding to these eigenvalues up to the point and try to pass to the limit at the point where it emerged from the imaginary axis. And I finish with that. I don't write anything, but I just go back to these eigen equation. I had certainly one written at some point. Yes, let's take that one. So it's not the exact same second order ODE that we have to deal with for our setting, but of similar form. And what's the important point about this? It has the form like a minus second derivative plus a potential times V. Okay. The problem is that the potential is complex, and that's what makes things difficult. Otherwise, it would be almost trivial. But when the eigenvalue, when the spectral parameter S goes to 0, this gamma becomes purely imaginary, and the whole thing becomes real. So if we could write the Rayleigh equation on the imaginary axis, it would be a real second order ODE, but with a singularity. Okay, otherwise it would be easy to pass to the limit. So the whole work then is to exclude solutions of a singular but real ODE. Okay, and try to match. It's a little bit more complicated than that, because a real ODE with a singularity, there is no dependence before, after the singularity and before the singularity. But because all of them come from solutions here just before the singularity that connect the point before and after the singularity, you can try to grab some information. And that's what you do in order to exclude these modes. And that's where this assumption in particular, where is my statement? That's where this assumption on the monotonicity of the Richardson functions enters into play. So there is an analysis there. I don't have time to discuss it, but it's just the analysis is less important than the way of proof, in a sense. We are stuck with a quadratic form which we cannot show to have a sign in a simple form. So we do some deformation to a simpler problem. Okay, and I think my time is at least over.